from Trivers's parental investment paper. And that kind of takes us a bit forward from the Bateman gradient. But still, we're in the kind of airy, kind of almost kind of theoretical realm of what we would predict to happen. And we're not quite there yet with how do we explain patterns on the ground. And that's where this paper by Emlen and Oring comes in. This is a beautiful, I really highly recommend going to read this paper. Again, it's one of those see the matrix papers where you're like, oh my goodness, that's how this all works. It's in Science. And they have two principles. Firstly, they talk about the operational sex ratio. We'll talk about that in the next slide. And then they have the principle that males follow females and females follow resources. And this links us through to the ecology of the species in question. And it's got really high explanatory power. And we'll see that in a second. So we're going to start with the operational sex ratio. Consider that example that I just gave. You've got 1-to-1 sex ratio in the population, 3 males and 3 females. But the operational sex ratio here is the ratio of individuals which are currently in the mating pool, by which I mean available for reproduction, available for mating. 2 of those females are unavailable, and so the operational sex ratio is 3 males to 1 female. And that is what determines the strength of sexual selection. It determines how competitive males need to be to get a mate, and it determines how choosy females are able to be over their mates. What factors contribute to the operational sex ratio? Well, I'm jumping ahead a little bit to this Coco et al. Paper, but which we'll go over a little bit later. But they have a lovely figure. One key feature here is the time in versus time out. There are time in, time out models, where time in refers to time in the mating pool, and time out refers to time spent investing in breeding. So time out would be parental care, or time for a male recuperating from the effort of breeding, time when you can't be looking for mates. And time in is the time when you're actively searching and competing for mates. And this wonderful kind of delightfully PowerPointed figure. I just pasted that straight in from this paper, and it kind of looks kind of hand drawn in PowerPoint using curves, etc. But it still illustrates a very nice point. So time in versus time out is one thing which determines your mating, your operational sex ratio. That's time in, time out models are one way of looking at it. Another way of looking at it is a slightly older idea from Tim Clutton-Brock and Jeff Parker, who looked at the ratio of potential reproductive rates. So that is how many offspring could you have in a world where you are not constrained by resources or partners? Like, what's the maximum possible reproductive rate for a male and the maximum possible reproductive rate for a female, and then look at the ratio of those. So we'll look at some examples in a minute, but some examples. So a kiwi, for example, here is a kiwi with her enormous egg, which is like practically the size of her own body, and she invests a huge amount of effort in producing this one massive egg, and so her potential reproductive rate is very, very small. Compare that with a female frog who produces thousands and thousands and thousands and thousands and thousands of eggs in frog spawn. Her potential reproductive rate is huge. It's on the order of the number of sperm that the males produce. So then we have a slightly more equal ratio of reproductive rates there. In some cases, the potential reproductive rate of males is less than the potential reproductive rate of females. That happens in these seahorses where the males give birth to live young. The male has a brood pouch, and the female deposits eggs inside the brood pouch, and the males fertilize them inside that pouch, and then they develop. The male gets pregnant and kind of spends a lot of time intensively caring for the developing offspring, and so it is the male that has the smaller reproductive rate, and so the investment is reversed. The roles are reversed in these seahorses. We'll talk about role reversal in a second. So operational sex ratio is a very important tool in thinking about what direction sexual selection operates in. Then you have the principle that males follow females and females follow resources. Now, in nature, consider what I said about anisogamy. The female is limited by how many offspring she can produce. And so what females want to do is to maximize the resources they get to produce offspring. So they tend to go to the places where the resources are best. So in space, like thinking on the order of the ecology of a species, if you've got patchy resources, the females will follow the resource patches to get to the places where they can maximize their offspring. The males, however, again according to the Bateman principle, are following the number of they want to maximize the mates. So they will go to a place where they can maximize the number of mates, which is where the females are. So you get a situation where females follow resources and males follow females. And the extent of female clumping, as we saw in the paper by Trivers, affects their monopolizability, the extent to which a male can control a group of females by any given male. The maximum kind of controllability of a group of females occurs at intermediate clumping, where females are in kind of manageable groups that one male can kind of dominate, one male can control, and not in a kind of a huge aggregation that one male cannot possibly control. We'll look at ramifications there in a second. But females can clump spatially, as in they can form little groups in space, or they can clump temporarily. For example, spatial is if resources are patchy. Temporal, for example, if they have to come together at a particular time to breed, if there's a breeding season. And both of these, this is the link. This is the link to what happens on the ground. This links through to a species' ecology. So let's have a look at how species with different ecology play out in terms of their mating systems. So you've got monogamy. You get monogamy in a situation where neither sex can monopolize the other. For example, where your resources are widely dispersed, you can't control a clump of resources, and individuals are widely dispersed, you can't control a clump of individuals. Or where breeding is continuous over the year, there's no particular breeding season where individuals are clumping together. Or where there's intensive biparental care, where neither sex is able to be off searching for mates because they're both tied to caring for offspring. For example, for goodness sake, gibbons are a good example of species where males and females have really large home ranges and they overlap entirely. So males and females are both on the same home range, and the pairs are widely dispersed. So there's no real point in deserting your partner to seek another mate because you're unlikely to meet anyone else with whom you might potentially mate. So it's rare to meet other ones. And so the male and female potential reproductive rate is pretty much similar. Neither would gain any benefit by deserting to find a different mate. And your operational sex ratio is effectively 1-to-1 as well. So it pays them to stick with each other and invest in raising the offspring that they can produce, rather than seeking other mates. On the other hand, instead of being widely dispersed, you could also have a situation where it takes two individuals to raise any offspring at all. So lots of birds have a situation where you just have intensive parental care. You have to incubate your eggs and you have to be off foraging to feed the offspring. It requires 2 parents to raise any offspring at all. And so your potential reproductive rate is pretty similar for both sexes, and the operational sex ratio is pretty much 1-to-1. Or is it? We'll come back, we'll put beans on that because we're going to come back to the situation in birds extensively later in the course. But 1-to-1, like monogamy comes from situations where operational sex ratios are pretty much 1-to-1. So that's monogamy. Then you have resource defense polygyny, where males defend patches of resources to which females come to visit to get those resources. So a good example of resource defense polygyny is elephant seals, where females have to come up onto a beach to breed, and they come in large numbers. They come in large numbers, and the male that wins the competition potentially stands to gain a massive amount of mating success. So males hold these harems on beaches that contain 50 plus females, so the successful male is able to defend to get a huge number of matings. And you get these very, very strong competitive fights, and often lethal fights among males for these harems of females. On the other hand, you have female wattled jacanas, where the females can lay more eggs than she can physically incubate. And then so what they do is they defend lily pads where harems of males all incubate some eggs. The eggs need incubation, but the female can physically lay more than she can incubate alone. And so she has a harem of males, each of which are incubating a clutch of eggs. And the female potential reproductive rate is therefore more than the male potential reproductive rate. And so females are there. There's then role reversal with the females competing for males. Very interesting. That's resource defense polygamy. Then you have, instead of resource defense polygamy, you can have a situation where you have female defense polygyny, where it's not the resources that are patchy, but it's the females themselves. So the females will form groups for some other reason, maybe defense against predators, or maybe shifting patterns of resources, or nesting aggregations. So in wild horses, the females form groups, form kind of wandering bands that go where the good forage is, and the males defend wandering bands of females. They're defending the females rather than defending the resources. Similarly, in bumblebee wolves, these Philanthus wasps, males will defend. The females nest in aggregations, and there's no particular pattern to where they nest, but the males will come and defend groups of nests, and the successful male that wins the competition will get all of the females in a given aggregation. That's female defense polygyny. I couldn't find a case of male defense polyandry. If you can find one in the literature, I would love to hear about it. But then you have, finally, you have something called male dominance polygyny, which is where males, it's almost a kind of a reverse situation where the males aggregate and have a competition among themselves to see who wins, and the females visit that aggregation in order to mate with the males. And this is something called a lek. There's an entire lecture on it by Domino. A really good example here is, oh, for goodness sake, a really good example here is the capercailles, black grouse, where males display at the lekking sites, and the dominant male goes to this very centre, and the females visit, and they always choose, the females overwhelmingly choose the winning male, and therefore the winning male stands to gain a massive number of matings, and anyone who's even slightly less than that winning male gets nothing. So the variance in male success becomes very, very high. There's one species, or one really good example of a very rare situation where females form leks, is the worm pipefish, And that paper there outlines, pipefish are a case where you have role reversal again, but in worm pipefish it's taken to extremes, and the females form leks to perform for males that choose the females. Really, really interesting. So you have a great spectrum of mating systems which are actually observable in nature, and the Emlen and Oring paper links back through to that. Like it helps you link ecology to the theory behind mating systems. Why? I just want a quick note about role reversal. Why do you get role reversal? Well, each of these papers that we've looked at has a different perspective on this. Bateman would say it's a situation where females gain more from extra matings than males, where the ecology provides a situation where females stand to gain more from getting extra matings than do males. We'll explore that in a second. Trivers would say it's where males are the ones which invest more per offspring for reasons dictated by the ecology. Think about the seahorses, where the males are becoming pregnant and investing a lot in each offspring. Cluttenbrock and Parker would say it's where the potential reproductive rate of a female is higher than the potential reproductive rate of a male. And Emlen and Oring would say it's where the operational sex ratio is reversed. All of these are more or less the same thing. Not exactly, but more or less. So effectively, that is the situation in which you would get role reversal. Some classic examples of role reversal are in seed beetles, Calissobruchus, where females will court the males. And the reason they're courting the males is because they are limited by food, and they get food from the males in the form of their ejaculate. So their sperm not only is used to fertilize eggs, but is also used as a nutritious gift, which can be up to 10% of the male's body weight. So in that case, a male is investing more than a female in reproduction. And so reproduction is more costly for males than it is for females, and males are now the limiting resource over which females have to compete. Another one is pipefish. We've met pipefish. Seahorses are a kind of pipefish as well, or at least very closely related to pipefish, where they have intensive male parental care. The females lay loads of tiny eggs, the males care for them. And so the Bateman gradient is reversed. It's the females that stand to gain more from mating, and the male that invests more in each offspring. That's sex role reversal.